Welcome to the Environmental Science and Engineering Podcast. Today, we're starting a new episode on one of the biggest environmental issues of our time, plastics, and their impact on our planet. Let's begin with the broad question. What makes plastics so dominant in our modern world?
Plastics represent a revolutionary class of materials that have deeply transformed almost every aspect of modern life. Their extraordinary versatility, durability, and cost-effectiveness made them a preferred choice across industries, from packaging and electronics to construction. But this widespread use has unintentionally led to one of the most urgent global crises: plastic pollution. It's now recognized as a serious issue affecting both natural and built environments worldwide.
So, to really understand how plastics became such a dominant force in modern life, I think we should take a look back. Could you walk us through the history of plastics? Where did this all begin?
Absolutely. The story of plastics actually starts long before the 20th century. Initially, humans relied on natural materials like animal horn or tortoiseshell, which have some polymer-like properties. But as industrial demand increased and natural resources became scarce, the focus shifted toward developing synthetic alternatives. The first major step came in 1869 with the creation of celluloid, often referred to as the first semi-synthetic plastic. But the real turning point was in 1907 when Leo Hendrik Bakelite invented Bakelite. This was the first fully synthetic plastic, a thermosetting resin that didn't rely on any natural polymers. That moment is widely regarded as the dawn of modern plastics.
Interesting. So it sounds like what started as a need to replicate natural materials ended up creating an entirely new class of materials.
Exactly. And what followed in the 1920s and 1930s was what we often call the plastics boom. During that time, materials like styrofoam and polyvinyl chloride, better known as PVC, entered commercial production. Then came polyethylene in 1933, known for its flexibility and strength, and nylon in 1935, which completely changed the textile industry. Teflon, or PTFE, came just a few years later, in 1938.
And then World War II, I suppose, accelerated that momentum.
Very much so. The 1940s saw an explosion in plastic production due to wartime needs. Materials like polyethylene proved to be strategically valuable, particularly in technologies like radar. Perhaps just as important was the advancement of injection molding techniques during this era, which allowed complex plastic parts to be mass-produced quickly and cheaply. That's when plastic manufacturing really scaled up globally. By the 1950s, plastic bags and synthetic fabrics like polyester became widespread. You had terms like drip dry and no iron becoming part of the cultural lexicon. And by 1976, plastics had overtaken every other material to become the most widely used substance in the world.
So we've covered how plastics evolved from natural substitutes to fully synthetic materials dominating nearly every sector. But I think there's another layer to this story, a more critical one. What drove this explosive development in the first place?
That's an essential point. The initial drive behind plastic innovation was the need to find alternatives to scarce or problematic natural resources. For example, ivory and tortoiseshell were expensive, limited, and often ethically controversial. So plastics were celebrated for their accessibility and affordability. They promised to democratize materials.
Right. So, in a way, they were seen as a solution to an environmental and economic problem.
Exactly. But here's where it gets complex. While the early innovations in plastic were indeed practical and even visionary, they came at a cost that wasn't immediately visible. The focus was almost entirely on short-term utility, cost-effectiveness, manufacturability, and speed of production, rather than long-term environmental persistence or end-of-life consequences.
So, basically, the very traits that made plastics revolutionary also sowed the seeds of our current environmental crisis.
That's correct. Plastics are incredibly durable, which is great for making long-lasting materials. But it also means they don't break down easily. Their moldability and low cost fueled mass production to such a degree that our global waste management systems couldn't keep up. This is a recurring theme in technological progress. Immediate gains tend to overshadow potential long-term systemic risks.
Now that we've discussed the historical and industrial rise of plastics, let's take a moment to define what plastics actually are from a material science perspective. What makes them so dominant in nearly every part of our lives?
Plastics are essentially synthetic polymers derived from petroleum-based sources. They are lightweight, durable, chemically stable, and highly moldable, which makes them incredibly versatile. These characteristics have made plastics a go-to material in fields like medicine, agriculture, and industrial manufacturing.
That versatility comes with a cost, though, doesn't it?
Absolutely. While plastics offer incredible convenience, especially in terms of production and application, they don't biodegrade easily. Their resistance to environmental breakdown means they persist for decades, sometimes even centuries in nature. And it gets more problematic when we consider that many plastics, especially those used for everyday items like plastic bags, forks, and packaging, are designed to be disposable.
So that brings us to the idea of single-use plastics, right? A term that's become almost synonymous with the throwaway culture we're now trying to push back against.
Exactly. These items, often used for just minutes, become part of a much larger problem. They symbolize the consume and discard mindset that has driven global plastic pollution. Their short lifespan in our hands is completely disproportionate to their long-term impact in the environment.
We've been talking about plastics in general, their history, their structure, and their widespread use. But now I want to dive into something more specific and, honestly, more alarming: microplastics. What exactly are microplastics and why are they such a growing concern?
Microplastics are tiny plastic particles that typically range in size from 0.1 to 1,000 micrometers. Unlike large plastic debris that we can see with the naked eye, microplastics are often invisible, but they're everywhere. What makes them especially concerning is how pervasive they are across all ecosystems.
And this concept of microplastics, it hasn't been around all that long, right?
That's correct. The term microplastics was first introduced in 2004 by marine biologist Professor Richard Thompson from the University of Plymouth. In his groundbreaking paper, Lost at Sea, Where is All the Plastic?, Thompson and his team showed that microscopic plastic fragments were already accumulating in the oceans as early as the 1960s. This was a major shift in how we viewed plastic pollution, from large, visible waste to microscopic contaminants.
Do we have any sense of the scale of the problem today?
Yes, and it's staggering. By 2014, estimates suggested there were between 15 and 51 trillion microplastic particles floating in the world's oceans, with a combined weight of anywhere from 93,000 to 236,000 metric tons. Today, microplastics and even smaller nanoplastics have been found in virtually every ecosystem on Earth, from remote Arctic tundras to vibrant coral reefs.
Wow, and how do these particles actually get into the environment? I mean, are they intentionally made that small?
They can be, and that brings us to the two major categories of microplastics. First, primary microplastics are manufactured in small sizes for specific purposes, such as microbeads in cosmetics or synthetic fibers in textiles. Second, secondary microplastics are formed when larger plastic items like bags, bottles, or fishing nets break down over time through physical abrasion and chemical degradation.
And which sources are contributing the most?
The largest contributor is actually vehicle tires. As tires wear down, they shed microplastic particles onto road surfaces, which are then washed into waterways via rain runoff, accounting for nearly 30% of global microplastic pollution. The second major source is synthetic clothing. During laundry cycles, materials like polyester and acrylic release microscopic fibers that pass through wastewater treatment systems and end up in aquatic environments.
So far, we've covered what microplastics are, where they come from, and how widespread they've become. But let's talk about the scientific side of this issue. When did researchers start paying serious attention to microplastics?
That's a great point. While the term microplastics was first introduced in 2004 by marine biologist Professor Richard Thompson from the University of Plymouth, widespread scientific interest in the topic didn't really take off until about a decade later. According to the literature, research into the presence of microplastics in aquatic environments saw a dramatic rise starting around 2015.
Do we know how extensive that growth in research has been?
Yes, and it's staggering. There are now over 6,000 published scientific articles specifically focused on the detection and presence of microplastics in water systems. What's even more striking is that more than 5,000 of those papers were published after 2017. That means the vast majority of our scientific understanding of microplastics is extremely recent.
Which really highlights how new and fast evolving this field is. We're just beginning to understand the full scale and implications of microplastics in our environment. We've talked about how widespread microplastics are, but let's now focus on what we can do about it. What kind of treatment methods exist today to remove microplastics from water?
That's a key question, and unfortunately, the answer is complex. Microplastics are incredibly resistant to degradation. Traditional plastics like PET and PVC are not biodegradable, and they can persist in the environment for hundreds or even thousands of years. So when it comes to water treatment, the goal isn't degradation, but rather effective separation and removal.
And I imagine the way these products are designed in the first place plays a role.
Absolutely. Many plastic products are made by combining different types of polymers, or by attaching plastics to other materials like glues or metal screws. This makes them difficult to separate, and as a result, very hard to recycle. That's why the concept of design for recycling is crucial. If products are designed with their end-of-life stage in mind, for example, using a single type of material or making them easier to dismantle, the quality of the separated waste streams improves, and recycling becomes both more efficient and economically viable.
Okay, but specifically for water treatment, what methods can actually remove microplastics?
There are a few. Coagulation and flocculation are commonly used pre-treatment processes. They work by aggregating small particles into larger ones that can settle out. And while they do help remove some microplastics, the efficiency is limited. Ultrafiltration, especially with membranes, has shown better performance. It can physically retain microplastics due to the small pore sizes.
What about filtration methods like sand filtration?
Sand filtration and other granular media filters do remove microplastics to some extent, but not entirely. Typically not close to 100%. And regarding oxidation processes, they're not a good option for microplastics. Plastics are chemically stable and require extremely strong oxidants and high temperatures for breakdown, which makes the process costly and impractical in large-scale water treatment plants.
So in short, while some conventional treatment methods help, there's still a gap, especially in achieving complete removal. So far, we've discussed what microplastics are, how they're formed, and even how they can be treated. But what about their actual effects on living organisms? What kind of damage can microplastics cause to animals and humans?
The effects of microplastics on living organisms are both physical and chemical. When ingested, microplastics can accumulate in the digestive system, leading to intestinal blockage, a false feeling of fullness, and impaired nutrient absorption. But it goes deeper than just mechanical obstruction. These particles often act like sponges for toxic chemicals, pesticides, heavy metals, and persistent organic pollutants, which can then be transferred to organisms upon ingestion.
So it's not just the plastic itself, but also what's stuck to it.
Exactly. And once inside the body, microplastics can trigger cellular-level effects. Studies have shown evidence of oxidative stress, inflammation, and even DNA damage in exposed cells. In animals, they've been linked to developmental issues and reproductive problems. In humans, although long-term research is still ongoing, there are concerns about endocrine disruption, immune suppression, and potentially even carcinogenic effects over time.
Given those risks, the next question is obvious. What can we do to reduce microplastic pollution?
First and foremost, we need to reduce our reliance on single-use plastics. Bags, bottles, straws. These items are major contributors. Increasing recycling rates is also essential, though it's not a silver bullet on its own. On the textile side, washing synthetic clothing releases microfibers into the water system. Using washing machine filters or special laundry bags can reduce that release significantly.
And what about cosmetic products?
Great point. Some personal care products, exfoliants, toothpaste, even some cleansers, still contain microbeads. Checking product labels and avoiding those with polyethylene or polypropylene as ingredients is one simple but effective step consumers can take.
So it's not only about consumer choices, right? What should happen on a larger scale?
Absolutely. Municipalities must improve waste management infrastructure to prevent plastics from entering the environment in the first place. On the industrial side, companies should be incentivized or regulated to switch to biodegradable alternatives. Public awareness campaigns, combined with strong policy and legal frameworks, are vital if we want to control microplastic pollution at its source.
We've talked about individual actions and technological solutions, but large-scale change often hinges on government and international policy. So what's being done at the policy level to combat plastic pollution?
There's actually been significant momentum over the last decade. One of the most comprehensive policy frameworks is the European Union's Single-Use Plastics Directive, adopted in 2019. This directive is a major pillar of the EU's broader plastic strategy and specifically targets plastic products that frequently end up as marine litter.
That's the one that includes bans on items like straws and cutlery, right?
Exactly. Since July 2021, items such as plastic straws, plates, cotton buds, and even food containers made from expanded polystyrene have been banned under this directive, provided there are sustainable alternatives. It also bans oxo-degradable plastics, which were once marketed as eco-friendly but don't fully biodegrade.
Are there any goals beyond just banning items?
Yes, the directive goes beyond bans. It sets mandatory recycled content targets. For example, plastic beverage bottles up to 3 liters must contain at least 25% recycled content by 2025 and 30% by 2030. There are also ambitious collection targets. 77% of single-use plastic bottles should be separately collected by 2025, rising to 90% by 2029.
That's a pretty aggressive timeline.
It is, and it's backed by extended producer responsibility schemes. That means companies producing these plastics are required to fund their collection and recycling. Labeling requirements have also been introduced to inform consumers about plastic content and the environmental impact of littering.
Interesting, but this is just the EU. What about actions from other parts of the world?
We've seen a global trend, especially regarding single-use plastic bans and microbeads. The U.S. banned microbeads in cosmetics back in 2015, and countries like the UK, Canada, and New Zealand followed suit. In terms of plastic bags, Bangladesh was actually the first country to ban lightweight plastic bags, as early as 2002, after devastating floods linked to clogged drains. Rwanda has one of the strictest bans, even prohibiting the import of single-use bags.
And how about countries with more moderate measures?
Many nations have adopted plastic bag charges rather than outright bans. As of 2018, at least 30 countries had implemented fees on lightweight bags, which not only reduce consumption but also generate revenue and preserve consumer choice. In the U.S., 12 states, including California, New Jersey, and Washington, have now banned single-use bags. There's also a federal goal to eliminate single-use plastic distribution by 2032.
Is there any effort to coordinate these policies globally?
Yes, there's increasing momentum for a legally binding global treaty on plastic pollution. Organizations like the Worldwide Fund for Nature are advocating for its conclusion by the end of 2025. The goal is to not just manage plastic waste, but to move towards a truly circular economy for plastics. Groups like the Ocean Foundation are pushing for treaty provisions that cover the entire life cycle of plastics, from design and production to disposal and reuse.
That's a significant shift. We used to treat plastic pollution mainly as a litter problem, like a beach cleanup issue.
Right, and that old narrative placed too much emphasis on individual responsibility. The more recent approach is systemic. Policies now ban problematic products, mandate recycled content, and require producers to take more accountability. The EU directive is a great example of this shift from reactive to proactive policymaking.
But are there any pitfalls in policy implementation?
Yes, and that's an important point. Poorly designed policies can have unintended effects. Take, for example, California. When they banned thin plastic bags, sales of thicker plastic bags, which weren't regulated, actually went up. These thicker bags were often not reused as intended, which in turn increased plastic waste. So policies need to be holistic. You can't just ban one thing and assume the problem is solved. You have to look at the entire material flow, anticipate behavioral responses, and ensure the infrastructure and incentives are in place to support genuine circularity.
We've come a long way in this episode. From the invention of plastics to the emergence of microplastics, their environmental and biological impacts, and finally to global policy actions. It's clear that while plastics were once hailed as a miracle material, their long-term environmental cost has been staggering.
Absolutely. What began as a solution to material shortages has evolved into a global crisis of durability and disposability. We've seen how plastic's very strengths, its resistance, its longevity, have become its greatest environmental flaws. And although technological solutions and individual behaviors are crucial, systemic policy changes and international coordination are essential to truly address the issue.
That's why we, as environmental engineers and researchers, felt it was necessary to prepare this episode using only peer-reviewed scientific studies and official data. We hope we were able to communicate this complex issue in a clear and thoughtful way.
And we'd love to hear from you, our listeners. What are your thoughts on plastic pollution? How do you think we can reduce microplastic contamination globally? Do you have any innovative ideas or examples from your region?
Please share your comments and insights below. We genuinely want to include diverse perspectives in this conversation. Also, don't forget to subscribe to our channel and leave a review. It really helps us continue producing science-based content.
This was the Microplastics episode of the Environmental Science and Engineering Podcast. We appreciate your time, and we'll see you in the next one.
Take care, and let's keep working together for a cleaner, healthier planet.